It feels like everywhere you turn these days, climate change and the need to switch to cleaner energy is staring us in the face, right?
Yeah, it's become this really big, unavoidable thing.
One of the biggest questions is like, can we actually power the entire planet with like 100% clean energy? Is that even a possibility?
Well, that's what we're diving into today. There's some fascinating research that goes way beyond just, hoping for a greener world.
Right.
It really digs into whether it's technically possible and, maybe even more importantly, if it makes economic sense to run everything on renewable energy.
So by everything, we're talking what? Like electricity?
Yeah, electricity, heating our homes, transportation, even things like desalination, turning seawater into drinking water, all by 2050.
Okay, that's a huge shift. So what are we basing all this on? Like, where's this information coming from?
Our main source is a super in-depth study.
Okay.
It lays out this pathway for a global transition to 100% renewable energy, and it focuses on making this whole thing affordable.
Cost effective, right.
Exactly. They didn't just look at one big energy system for the whole planet.
Ah, okay.
They actually analyzed 145 different energy systems around the world.
Wow, 145. So they're acknowledging that what works in, say, Iceland might be totally different from what works in, like, Arizona.
Yeah, exactly. And they didn't stop there.
Okay.
They combined these 145 systems into 9 major global regions to get a more complete picture.
So for everyone listening, what's the most important thing to keep in mind as we go through all this?
I think the big takeaway here is that a sustainable energy future, like one that doesn't wreck the planet, isn't just some, pie-in-the-sky dream.
Right.
This research actually shows that it's possible and that it could even end up being cheaper and more efficient than our current, fossil fuel-heavy system.
Okay, so that's a big statement, cheaper and more efficient. I mean, this study must have gotten into some serious detail to make those kinds of claims.
Oh, absolutely.
What kind of detail are we talking?
They did this really impressive thing where they looked at energy supply and demand for each of those 145 systems every hour.
Every hour.
Yeah, so they're accounting for the fact that, the sun doesn't always shine, the wind doesn't always blow. They factored that variability right into their calculations.
So it's not just like average yearly numbers, they're looking at the real-time fluctuations.
Exactly. They're getting really granular with it, which I think makes the results even more convincing.
Okay, so let's step back for a minute and talk about why this whole transition is so important. We hear a lot about climate change and reducing emissions. What does this study say about the urgency of moving away from our current energy system?
Well, they start by laying out, just how much our current reliance on fossil fuels is contributing to greenhouse gas emissions. And they make it really clear, like crystal clear, that we need a fundamental change if we're serious about meeting global climate goals.
Like the Paris Agreement and all that.
Exactly. They see this transition as essential for meeting those commitments.
And it's not just about cutting emissions, is it?
No, not at all. They also point out that this kind of energy switch could lead to some other pretty big wins.
Like what?
Well, for one, they estimate that we could potentially save something like 50% of the total energy we currently use.
50%. That's a huge amount. How is that even possible?
A lot of it has to do with efficiency. Electric technologies like electric cars and heat pumps are just inherently more efficient than burning things like gasoline or natural gas.
Right, because you're not losing energy in the combustion process and all that.
Exactly. Plus, renewables themselves don't have the same losses associated with, extracting and transporting fossil fuels.
Right, you don't have to dig up coal or drill for oil.
Exactly. It's a much cleaner process from start to finish.
And this study also mentions something about everyone having access to clean water and affordable energy. How does that fit into this whole picture?
That's a really important point. A lot of traditional power plants use a ton of fresh water for cooling. Switching to renewables like solar and wind would significantly reduce that water usage, which is becoming more and more critical as water scarcity increases around the world.
Yeah, that makes sense.
And on the affordability side, the cost of renewable energy technologies, particularly solar, has been plummeting, which means the overall cost of producing and using energy could actually come down, making it more accessible to a lot more people.
So it's not just good for the planet, it could be good for people's wallets, too.
Exactly. It's a win-win situation in a lot of ways.
Now, we've all heard about different approaches to tackling climate change and energy. Some people say we need to capture carbon from fossil fuel plants. Others say we need more nuclear power. What does this research say about those kinds of solutions?
This is where things get interesting. The study actually pushes back against those ideas a bit.
Oh, okay.
They point out that a lot of existing global energy plans still rely on those technologies, things like carbon capture and storage or nuclear power, but they see those as having some big question marks around their long-term sustainability.
So they're not totally dismissing them, but saying maybe we shouldn't be putting all our eggs in those baskets.
Right, they're saying there might be better, more sustainable ways to go about this.
Okay, and they also compare their findings to other studies that suggest we need to drastically reduce our overall energy consumption.
Yeah, there's this whole debate about whether we can solve the climate crisis without, like, using a lot less energy overall.
Right, because some people say we need to fundamentally change our lifestyles.
Exactly. This study actually looks at scenarios where final energy demand continues to grow. They do see huge efficiency gains, but they're not assuming we need to go back to, like, pre-industrial levels of energy consumption.
So their approach is more about using energy smarter and cleaner rather than just using a lot less of it.
Yeah, I think that's a fair way to put it.
And they're not alone in this, right? They mention other studies that have come to similar conclusions about renewable energy.
Yeah, they reference a bunch of global studies that, using different methods and assumptions, also show that renewable energy systems can be cost competitive by 2050. And importantly, they highlight the fact that these renewable systems can bring all sorts of benefits beyond just, cost and emissions reductions.
Okay, like what kinds of benefits?
Things like creating more jobs, particularly in manufacturing and installation, and reducing things like air and water pollution, which also have big costs for society.
So it's a much broader picture than just, CO2 levels in the atmosphere.
Right, it's about a whole system change with potentially far-reaching positive impacts.
So with all that in mind, what makes this particular study stand out? What's new or unique about their approach?
They emphasize a few key things. First, they look at multiple energy sectors together. It's not just about electricity, it's about power, heating, transportation, and even desalination. They analyze all of that within one comprehensive framework.
So they're really looking at the big picture, how all these pieces fit together.
Exactly. And then that incredible level of detail, looking at things hour by hour.
Right, we talked about that earlier.
That's crucial for really understanding the challenges and opportunities of relying on variable renewables like solar and wind. They also really dig into how these different energy sectors can work together, what they call sector coupling.
Like using excess solar power to create hydrogen for fuel cells, that kind of thing.
Exactly. And they even factor in water scarcity, which is going to become a bigger and bigger issue as the climate changes.
So they've created this really elaborate model to figure all this out. Tell us a bit more about how this model actually works.
At the heart of it is what's called the LUT Energy System Transition Model. Yeah, it's named after the university where it was developed, Lappeenranta University of Technology in Finland. It started out as a way to study the power sector, but they've expanded it to cover all those key energy areas we've been talking about: power, heating, transportation, desalination, across those 145 different regions around the world.
145 regions, wow. And you said earlier it's a bottom-up approach. What does that mean in this context?
It means they're starting at the local level. The model looks at each region, sees what renewable resources are available there, sunlight, wind, hydropower potential, and then figures out the most cost-effective way to meet the energy needs of that specific region using those resources.
So it's not like some central planner dictating what everyone should do. It's more about letting each region optimize for its own circumstances.
Right, and then once they've done that for all 145 regions, they aggregate the results to look at 9 major global regions and then ultimately a global overview.
Okay, so it's local solutions adding up to a global picture. And the model looks at things hour by hour, which you said is really important for understanding the impact of variable renewables. Why is that so crucial?
Think about it like this. If you just look at average yearly numbers, you might think, okay, we have enough solar and wind power to meet our needs. But in reality, the output from those sources fluctuates a lot throughout the day and throughout the year.
Right, the sun sets, the wind dies down.
Exactly. So this model, by looking at things hour by hour, can really assess how big of a deal that variability is and how much storage and grid interconnection we'll need to keep the lights on, so to speak.
So it's about matching supply and demand in real time, not just on paper.
Precisely. It's a much more sophisticated approach than some older models that use like these simplified time slices.
And the main goal of all this is to find the lowest cost way to achieve 100% renewable energy.
That's the primary driver. The model is essentially trying to figure out, given all these constraints and assumptions, what's the most cost-effective way to meet all of our energy needs using only renewable sources.
And when we talk about energy, it's not just electricity, right? What other forms of energy does this model consider?
No, it goes way beyond electricity. They include electricity, of course, but also heat at 3 different temperature levels, which is important because different industrial processes and buildings need different temperatures.
Right, like you need a lot hot to heat to melt steel than to heat your house.
Exactly. And for transportation, they include hydrogen, both as a gas and a liquid, methane in both forms as well, and even things like gasoline and jet fuel, at least in the transition period.
So they're acknowledging that we can't switch everything over to like batteries and fuel cells overnight.
Right, there's a whole transition process involved, and they try to capture that in the model.
And you mentioned this two-stage simulation process. Can you explain what that involves?
Yeah, so we actually run the model in two phases. The first phase focuses on individual energy consumers, or presumers. These are people or businesses that might have their own solar panels on their roof, or a small wind turbine.
Okay, so they're generating at least some of their own power.
Right, so the model first figures out for each of these presumers what the most cost-effective mix of energy sources is for them, given their own generation and the local energy prices. Then the second phase takes all that information about individual presumers and uses it to optimize the overall energy system for each of those 145 regions.
So it's like a micro and macro approach combined.
Yeah, I think that's a good way to put it. They're getting both the individual level detail and the big systems level picture.
And when they talk about costs, they're including everything, right? From building new power plants to the cost of the fuel itself.
Yeah, they try to be really comprehensive with their cost calculations. They include the yearly cost of all the infrastructure, like power plants, transmission lines, storage facilities, all of that, plus the operating costs like maintenance, fuel costs where they apply, and even the cost of greenhouse gas emissions.
And the cost of emissions is going to go down as the system gets cleaner, obviously.
Right. It's really meant to reflect the full economic picture of this energy transition.
It sounds like a very robust model. They even compared it to other similar models that are out there.
Yeah, they actually benchmarked their model against some other well-known long-term energy transition models.
And how did it stack up?
It actually performed really well. They found it was more detailed and transparent than many of the other models, particularly when it came to how it dealt with time, geographic variations, the different technologies it included, how it linked different energy sectors together, and just the overall transparency of its assumptions and calculations.
So they're not just making things up, they're basing it on solid research and analysis.
Exactly. They're being very rigorous about it.
Okay, so we have a good sense of the model itself. Now let's get into the nuts and bolts of this 100% renewable world. What are the specific technologies that are going to power this future?
They break it down into 6 main categories: electricity generation, heat generation, transportation, energy storage, sector coupling, and electricity transmission.
Okay, that covers pretty much everything. Let's start with electricity generation. What kind of renewable sources are we talking about here?
It's a pretty diverse mix. For electricity, they consider solar PV in all its forms, rooftop panels, utility-scale solar farms, even things like solar panels that track the sun throughout the day. They include wind power, both onshore and offshore.
Okay, those are kind of the usual suspects these days.
Yeah, but they also factor in hydropower, both from run-of-river systems and reservoirs, geothermal energy, and various forms of bioenergy.
Bioenergy, so that's like burning wood or crops for electricity.
It can be, but it also includes things like biogases from landfills and waste-to-energy plants.
Okay, so it's a pretty wide range of renewable sources. What about heat generation? How do we heat our homes and businesses in this 100% renewable world?
For heating, they look at both district heating systems, which are more common in Europe, and individual heating solutions for homes and buildings.
So like a central boiler for a whole neighborhood versus a furnace in your basement.
Exactly. And for district heating, they consider things like large geothermal plants, big solar thermal systems, biomass power plants, and even large-scale heat pumps that can extract heat from the air or the ground.
Okay. And what about for individual homes and businesses?
For those, they look at smaller heat pumps, electric resistance heaters, and biomass boilers. They also consider concentrating solar power for some industrial heat applications.
Concentrating solar power, so that's like those giant mirrors that focus sunlight to create heat?
Yeah, exactly. That technology has a role to play too.
Okay, so we've got electricity and heat covered. Now, what about transportation, which is like the elephant in the room when it comes to emissions?
Yeah, transportation's a big one. They break it down into 4 main categories: road, rail, marine, and aviation.
Okay, that makes sense. And what are the options for each of those?
So for road transport, they look at everything from cars and trucks to buses, and they consider a mix of powertrain technologies. Obviously, traditional gasoline and diesel engines are still in the mix in the early years.
Right, because we can't just scrap all the existing cars overnight.
Exactly. But they also include plug-in hybrid electric vehicles, fully electric vehicles, and fuel cell vehicles that run on hydrogen.
Okay, so a gradual shift toward cleaner options over time. What about trains?
For trains, they consider both traditional diesel-electric locomotives and fully electric trains that get their power from overhead lines or a third rail. For shipping, they look at a mix of options too, including electric motors powered by batteries or fuel cells, ships that run on liquefied natural gas, and even ships that use biofuels or synthetic fuels.
LNG, that's still a fossil fuel, isn't it?
Yeah, but it's considered a cleaner burning fossil fuel than traditional bunker fuel, so it's often seen as a bridge technology. And then for aviation, which is probably the hardest sector to decarbonize, they look at the potential for electric planes, hydrogen-powered planes, and planes that use advanced biofuels or synthetic fuels.
Okay, so a lot of different possibilities depending on the specific application. And to make all this work, especially with variable renewables like solar and wind, we need a way to store energy. What storage technologies did they consider?
They looked at a whole range of storage technologies, from short-term to long-term. For short-term storage, the main players are batteries and pumped hydroelectric storage.
Pumped hydro, that's where you pump water uphill when you have excess electricity and then let it flow downhill through a turbine to generate power when you need it, right?
Exactly. It's a well-established technology that can store a lot of energy. For medium-term storage, they include things like compressed air energy storage and thermal energy storage, which can store heat at different temperatures.
Okay, and what about for storing energy for longer periods, like seasonally?
For that, they look at power-to-gas technologies, where you use excess renewable electricity to produce hydrogen or methane, which can then be stored in tanks or underground caverns and used later to generate electricity or heat.
You're essentially turning electricity into a storable fuel.
Right. That's a key part of making this whole system work.
And you mentioned sector coupling earlier, which is all about integrating different parts of the energy system. Can you give us some specific examples of what that involves?
Sure, one key area is fuel synthesis, which is essentially using renewable electricity to create fuels that can be used in transportation or industry.
Like making hydrogen from water and then using that hydrogen to make synthetic fuels.
Exactly. And they also consider power-to-heat technologies like heat pumps and electric resistance heaters, which can shift heating demand away from fossil fuels.
Right, so instead of burning natural gas to heat your house, you're using electricity generated from renewables.
Right. And they also include heat-to-power technologies, which can capture waste heat from industrial processes and use it to generate electricity.
So you're basically squeezing more useful energy out of the system.
Exactly. It's about using energy as efficiently as possible. And they even include things like desalination and water pumping in this sector coupling category, because those can be integrated with the power grid to provide flexibility and help balance supply and demand.
Okay, so it's a really comprehensive approach. And last but not least, what about the infrastructure needed to actually move all this renewable electricity around?
For transmission, they look at both high-voltage AC and DC power lines, as well as the converters needed to connect different parts of the grid.
AC and DC, so that's like the difference between the electricity in your house and the electricity that comes from a battery.
Yeah, that's a good analogy. Different parts of the grid use different types of current, and you need converters to make them compatible.
Right, and these long-distance transmission lines are going to be crucial for getting renewable energy from where it's generated to where it's needed.
Absolutely. It's all about connecting the dots, so to speak.
Okay, so they've got all these different technologies in their model. Where did they get the information about how much these things cost and how well they perform?
Their primary source for a lot of the technical and economic data is the European Commission, but they also draw on a whole bunch of other sources like the International Energy Agency, industry reports, academic research.
So it's not just based on like one set of assumptions. They're looking at a wide range of sources.
Exactly. They're trying to be as comprehensive as possible.
And these assumptions about cost and performance, they change over time in the model, right?
Oh, absolutely. Technology doesn't stand still, so they update these assumptions in 5-year steps, all the way to 2050, to reflect the expected improvements and cost reductions in all these technologies.
So they're building in the idea that solar panels are going to be cheaper, batteries are going to get better, that kind of thing.
Right. They're trying to capture those learning curves that we see in technology development.
And when it comes to big infrastructure projects like this, the cost of money is a huge factor. What interest rate did they use in their calculations?
They used a weighted average cost of capital, or WACC, of 7% for most technologies. But for residential solar PV systems, they actually used a lower rate of 4%, because homeowners and businesses typically have different financing options.
So they're trying to reflect the real-world conditions for borrowing money.
Exactly. They acknowledge that using different interest rates for different regions could make their model even more accurate, but there's just not a lot of good data on how borrowing costs are going to evolve in different countries.
Makes sense. And what about electricity prices? How did they predict what those will look like in the future?
They used historical data on retail electricity prices for different consumer types, residential, commercial, industrial, and then projected those prices out to 2050, taking into account things like changes in the cost of generation, grid infrastructure costs, and government policies.
So they're factoring in things like carbon taxes or renewable energy subsidies.
Right. All those things can impact the final price consumers pay.
And one last detail on the financial side. What happens to the electricity generated by all those rooftop solar panels we talked about earlier? Like, if someone's generating more than they're using, do they just give it away?
No, they don't give it away. The model assumes that any surplus electricity produced by these small-scale producers, these prosumers, is fed back into the grid at a fixed price of zero point zero 0.02 euros per kilowatt hour. And they make sure that these prosumers always prioritize their own needs before exporting any excess to the grid.
So they're not forced to sell their electricity if they need it themselves.
Exactly. It's a fair system for everyone involved.
Okay, so we've covered the supply side, the technologies, and costs. Now let's talk about the demand side. How much energy are we actually going to need in the future? How did they figure that out?
For electricity demand, they mostly use projections from the International Energy Agency, supplemented by data from local sources, and they adjusted those projections to account for losses in transmission and distribution.
Right, because you always lose some electricity when you send it over long distances.
Exactly. For heating demand, they relied on a recent report that looked at global heat demand trends. For desalination, they used estimates from research in that specific field. And for transportation energy demand, they used projections from various studies that looked at how people and goods are likely to move around in the future.
So they're drawing on a wide range of sources to get a handle on how much energy we're going to need in different sectors.
Yeah, they're trying to capture all the major factors that are going to drive energy demand going forward.
And what about the renewable resources themselves? Sunlight, wind, water flow. How did they determine how much of that we could realistically capture?
For solar and wind, they used historical weather data to calculate something called capacity factor profiles.
Capacity factor, what does that mean?
It's basically a measure of how often a power plant is actually generating electricity. So for solar, it's how many hours of sunlight you get in a given location, taking into account things like clouds and the angle of the sun. For wind, it's how often the wind is blowing at a speed that allows the turbines to generate power.
Okay, so they're using real-world data to figure out how much energy we could actually get from these sources.
Right. And they did something similar for hydropower, using monthly data on river flows to estimate how much electricity could be generated from hydropower plants.
What about bioenergy? That's renewable, but there are questions about how sustainable it really is.
Yeah, that's a valid concern. They break down their estimates for sustainable biomass resources into several categories, including solid waste, recipes from agriculture and forestry, and feedstocks for biogas production.
So they're not just assuming we can burn all the trees in the Amazon.
No, they're taking a more nuanced approach. They assume high recycling rates to limit the amount of waste available for burning. They assume high collection rates for things like food scraps and manure that could be used to make biogas. And they include the costs associated with collecting and processing these biomass resources, including things like gate fees at landfills.
Okay, so they're trying to be realistic about the potential and the cost of bioenergy.
Exactly. And for other resources that are more location-specific, like geothermal energy and the potential for compressed air energy storage, they used established methods to estimate the available resources in different regions.
So they've built this incredibly detailed model. They've pledged in all these assumptions about costs, performance, resource availability, and energy demand. What happens when they run this model? What does the future look like?
One of the most striking results is their projection for electricity demand. They see a dramatic increase in electricity demand, driven by two main factors, electrification and economic development, particularly in developing countries.
Electrification, meaning we're using electricity for more things than we do now.
Exactly. Things like electric vehicles, heat pumps, electric industrial processes, and even desalination are all contributing to this increase in electricity demand. And at the same time, as developing countries grow their economies, they're going to need more energy overall.
So we're using more energy, but a much bigger chunk of it is coming from electricity.
Right. The model predicts a significant shift towards both direct and indirect electrification. Direct electrification is things like plugging your car into the grid. Indirect electrification is using renewable electricity to create other energy carriers, like hydrogen.
And this shift towards electrification is a key part of the energy efficiency gains they're seeing, right?
Absolutely. Electric technologies are generally much more efficient than their fossil fuel counterparts, so as we electrify more and more of our energy use, we get more bang for our buck, so to speak.
So we're using more energy services, but we're not necessarily using more energy overall.
Right. They estimate that we could potentially achieve energy savings of around 49% by 2050, compared to if we just continued on our current path.
Wow, 49%. That's a huge number. And those savings are the same everywhere in the world.
No, it varies a lot depending on the region. Regions that are already quite efficient, like some parts of Europe, see smaller gains. But regions that rely heavily on inefficient fossil fuel-based systems, like some oil-producing countries, could see the biggest savings.
So there's a real opportunity for some countries to leapfrog over older, dirtier technologies.
Absolutely. They have a chance to build a clean, modern energy system from the ground up.
You mentioned that they use a specific method for calculating these energy savings?
Yeah, they use what's called the physical energy content method, or PECM. It's a way of accounting for the total amount of energy we extract from natural resources, which makes it easier to compare different fuels and technologies on an apples-to-apples basis.
Okay, that makes sense. And they also looked at how much energy each person is using on average, even with a growing population.
Right. They actually see a slight decrease in per capita primary energy demand, even though total global energy demand is increasing.
So we're becoming more efficient overall, even as the population grows.
Exactly. It's a sign that we can decouple economic growth from energy consumption.
One of the concerns about relying on renewables is that they're intermittent. The sun doesn't always shine, the wind doesn't always blow. What does the study say about how we deal with that variability?
They found that by using a mix of storage technologies and demand-side management, you can actually keep the amount of wasted renewable energy pretty low.
Demand-side management, meaning you shift some of your energy use to times when renewables are plentiful.
Right, like charging your electric car at night when solar power is less available. They estimate that only about 3.5% of total renewable electricity generation would be curtailed in 2050.
Curtailed meaning it's just not used because there's no demand for it at that moment.
Exactly. So it's a very manageable amount of waste, especially compared to, say, other challenges we're facing.
Okay, so the high electrification scenario looks promising in terms of efficiency and emissions. Now let's talk about how we actually get there. What are the big changes that happen in our energy system between now and 2050?
The model shows a really dramatic shift in how we generate electricity globally. We go from a system dominated by fossil fuels in 2015 to one where almost all of our electricity comes from renewables by 2050.
And what's driving that change?
The main driver is the falling cost of renewable energy technologies. They become so cheap that it just doesn't make economic sense to keep building new fossil fuel power plants.
Okay, so economics is playing a big role here.
Absolutely. It's becoming cheaper to go green.
And which renewable technology really takes the lead in this transition?
Solar PV really emerges as the dominant source of electricity globally. It grows from just a tiny fraction of global electricity generation in 2015 to a whopping 76% by 2050.
Wow, 76%. That's a massive increase. And what about wind power? It's been growing pretty rapidly in recent years.
Wind power plays a really important role in the early stages of the transition. It peaks at around 42% of global electricity generation by 2030, but then its share starts to decline as solar PV becomes even more cost competitive.
Okay, so it's not like wind power goes away, it just gets overshadowed by solar.
Exactly. It still plays a significant role, especially in regions with good wind resources.
And what about the other renewables, hydro, geothermal, bioenergy?
They have smaller shares in the overall global mix, but they still contribute, especially in regions where those resources are abundant.
Like hydropower in Norway or geothermal energy in Iceland.
Right. They each have their own niches where they make the most sense.
And what happens to fossil fuels and nuclear power in this scenario?
They essentially get phased out completely from electricity generation by 2050. The model shows that they just can't compete economically with renewables.
So it's not just about shutting down coal plants, it's about not building any new ones either.
Right. It's a gradual but ultimately complete transition away from those sources.
And as all this electrification happens, the overall supply of electricity is going to have to increase dramatically, right?
Absolutely. Global electricity supply grows by a factor of like 5 between 2015 and 2050.
Wow, 5 times as much electricity. And a lot of that growth is happening in developing countries, I imagine.
Yeah, they're electrifying their economies and providing energy access to more people, so their electricity demand is growing very rapidly.
Okay, so we've talked a lot about electricity. What about heat generation? Does that undergo a similar transformation?
It follows a similar pattern, but it's a bit slower. Global heat generation also shifts from being heavily dependent on fossil fuels to being dominated by electric and renewable sources by 2050. Heat pumps become a really big player in this transition, both for district heating systems and individual building heating.
So instead of burning natural gas to heat your house, you're using a heat pump powered by renewable electricity.
Exactly. It's a much cleaner and more efficient way to heat buildings.
And this shift towards electrifying heating and transportation, that's really what drives the whole decarbonization of the energy system, right?
Absolutely. As we electrify those sectors, the demand for electricity goes up, which creates more incentives to build out renewable energy capacity. And that, in turn, makes it easier to phase out fossil fuels in the power sector itself. It's all interconnected.
It's like a virtuous cycle.